In this video, we introduce our work about the pixel pair occlusion relationship map and its application in depth refinement. We focus on oriented occlusion boundary estimation task, which is a harder task than just estimating occlusion boundaries. Given an image, the goal is to estimate simultaneously occlusion boundary and a boundary orientation which indicates the side of foreground and background. As we can see, the left side of green arrow indicates foreground. Our method is based on one key idea which makes a whole difference, classifying the occlusion status of neighbor pixel pairs, rather than just doing pixel-wise detections. Experiments on a variety of datasets demonstrate that our method outperforms existing ones on this task. Here are two qualitative results where the correctly estimated pixels in predictions are colored green. Compared to the state-of-the-art method OFNet, we achieve better results. Owing to the proposed formulation, the occlusion orientation we infer can be used to sharpen depth maps and consistently improve the performance of state-of-the-art molecular depth estimation methods. Compared to the initial estimation by SharpNet, which targets at sharp depth boundaries, our method not only sharpens depth maps on boundary regions, but also recover depth discontinuities which are not detected in the initial estimation. To train our models, the occlusion ground truths are generated based on our method, which locally approximate thin surfaces at order 1 using depth map. This proves to be superior both to a direct thresholding on depth difference and to edge detection on depth map. The good quality of generated occlusion information allows us to learn much better models. To illustrate the method, we firstly formalize geometric occlusion in a single image based on thin geometry information. Given a camera located at C and two thin 3D surfaces S1 and S2, geometric occlusion can be defined locally as one surface S1 comes before another surface S2 along a ray L from C. Given an image plane, we assume that each pixel in the image plane is the 2D projection of a visible 3D surface patch, and the center of this pixel is the 2D projection of a 3D point on this surface patch. Here we use a pixel P to represent the surface patch SP, and SP belongs to the surface S1. Likewise, we can use another immediate neighbor pixel Q to represent partially the visible part of surface S2. The geometric occlusion between surfaces S1 and S2 can therefore be interpreted locally as the occlusion relationship between surface patches SP and SQ. In this case, SP occludes SQ and the pixel P occludes pixel Q in the 2D image. Typically, what we have is an RGBD dataset. It contains RGB images, relevant depth maps, and surface normal maps, which offer information about visible surfaces locations and orientations. To generate occlusion relationship ground truths between surface patches, we firstly approximate surface patches SP and SQ by their tangent planes πP and πQ, and propose a generation method which considers simultaneously tangent plane locations and orientations. Our method considers different occlusion configurations, and it enables the generation of datasets with accurate ground truths for training and testing. As we can see, compared to directly thresholding depth difference, our method reduces greatly false positive occlusion boundaries. Please refer to our paper for more details. As the occlusion relationship is naturally pairwise based on our definition, we therefore propose a pixel pair occlusion relationship map to cover occlusion relationships in 2D images. To illustrate, we consider an image which consists of foreground region colored yellow and background region colored blue. The pixel pair occlusion relationship map is illustrated here, and the pixel pairs with occlusions are connected by colored arrows which indicate occlusion directions. Here we can see 4 colors as there exist 4 inclinations for pixel pairs in a connectivity 8 neighborhood. Pioneering work proposes figure ground notion to represent occlusion boundary ownership, where boundary pixels are labeled as either foreground pixels or background pixels. Compared to this representation, a pixel in pixel pair occlusion relationship can be simultaneously foreground pixel and background pixel, with reference to different neighbor pixels. Our formulation can therefore offer richer occlusion information. Because of the originality of our formulation, there is no other method to directly compare it. We therefore propose a method to convert our occlusion formulation to oriented occlusion boundary representation to compare with recent methods. This conversion is possible as both these two representations share pixel-wise occlusion direction information. To model the proposed occlusion relationship between neighbor pixels PQ, we use a random variable omega PQ to represent the three possible occlusion status. P occludes Q, P is occluded by Q, and no occlusion between P and Q. As we have four inclinations for pixel pairs, our formulation can be stored with four 2D label maps. As shown in the right part of this slide, the three occlusion status labels are colored red, white, and blue respectively in each label map. For occlusion relationship estimation, we adopt a labeling approach like segmentation. We classify each valid pixel pair by scoring its three possible occlusion status. The model takes an image as input and outputs four label maps covering four inclinations. We adopt a unite-like autoencoder architecture with a ResNet encoder for our estimator. As our approach is not bound to a specific architecture, we may benefit from improvements in general segmentation methods in the future. To train the model, we use a class-balanced cross-entropy loss for each segmentation task. We evaluate an oriented occlusion boundary detection benchmark. The first two metrics measure the F-scores of oriented occlusion boundary with different thresholding methods, while the last metric measures the average precision of all occlusion probability thresholds. Compared to state-of-the-art methods, our method achieves better performance on all three metrics on BSDS ownership dataset, which captures outdoor scenes. To further validate our method for indoor scenes, we also generate grand truths from two indoor scene RGBD datasets and name them NYU-V2OR and IBEAMS-1OR. Our method once again outperforms other methods. To illustrate the value of proposed occlusion relationship formulation at the middle level representation, we design a depth map refinement module. Given estimated occlusion relationships and an initial depth estimation, our model outputs a refined depth map. We again use a unite-like architecture with SCAP connections for our model. To train the model, we penalize regions in the refined depth map, where the pixel pair depth differences are not consistent with the grand truth pixel pair occlusion relationships. We evaluate our depth refinement module on two RGBD datasets with global matrix and boundary matrix. As the fraction of occlusion boundary regions pixels in each image is rather small, the refinement on global matrix is not visible. Here we show refinement on boundary matrix, which measure depth boundary estimation accuracy error and completion error. The initial depth estimation errors are colored blue, and the current state-of-the-art depth boundary refinement method errors are colored orange. Compared to these two estimations, our method colored green consistently reduces depth estimation errors across different molecular depth estimation methods. As shown by the results on depth refinement, our pixel pair occlusion relationship can serve as a good middle-level guidance signal for scene understanding task. Thank you, and please refer to our project webpage for more details.